talk a little bit about sort of pushing some stuff I've been doing on the cloud feedback and really trying to drill down into not just what's the global average feedback, but where is the cloud feedback coming from and what clouds are driving the cloud feedback. So let me just sort of go over the methodology of how we do this. So this is a plot of top of atmosphere flux anomaly. So we've taken out the seasonal cycle. It's global average. It's monthly average. It's from series, and it's a mess. That's just what it looks like. I think the data are right, but you don't see a lot in there that you recognize. Positive fluxes are downward, so that's just the sign convention I'm using. Now, you take this, and what we want to do is we want to break this into components. We know that the variation in top of atmosphere flux is due to a few things: changes in temperature through sigma T to the fourth, changes in water vapor, since water vapor absorbs infrared radiation, changes in albedo has a big effect on shortwave, changes in cloud, and then forcing. And essentially, we want to focus on this term right here. We want to isolate what part of the series data is caused just from clouds. And so basically, how do you do that? Well, I'm going to use a method that Brian Soudan and Karen Schell both published in 2008. And basically, here's a picture of the Earth. And so imagine you have a satellite going around. It's measuring the top of atmosphere flux on the Earth. And it's measuring short and long wave radiation. And now imagine that you took all the clouds away. And then you had another satellite that measured the flux with no clouds. Everything else was exactly the same. The only difference is that there were no clouds on this planet. Well, the difference of the flux you'd measure is what we call the cloud radiative forcing. So it's the difference between the clear sky, the flux of the clear sky Earth, and the flux for the all-sky Earth. The all-sky Earth is one that has clouds. And the difference is a measure of the impact of clouds. So essentially, we're going to use clear sky, comes from series, so it measures. So on all the cloud information is in the clear sky fluxes, so that's measured. And then the all-sky we're going to get from a reanalysis, and I can talk about that offline if you want to know why I did that, etc. But the difference is the impact of clouds. And then what I'm going to do is we're going to take the cloud radiative forcing suitably adjusted per Soudan and Schell to account for non-cloud effects. And I'm going to regress that against the surface temperature. And the slope of that regression is the feedback, is the cloud feedback. So I'm just looking at, put it in different words, I'm looking to see how the energy trapped by clouds changes as the climate changes. And so, and so when you do that, you need some temperature variations. You need some dynamic range along the x-axis. And this is the temperature for the last 10 years. And you see that there are things like El Niños and La Niñas. That's really where you get your dynamic range. And so the feedback I'm really deriving comes from ENSO events mainly, and weather noise and things like that. There's not a lot of climate change. Just you can sort of tell by eye there's not a lot of climate change, and in any decade you don't see climate change compared to other events, other sources of variability. So when we put all that together, this is what you get, and it looks a bit like a mess, but nonetheless you can do statistics on it, and you can see that the slope is positive of the energy trapped by clouds versus surface temperature. And that suggests that in the global average, there is a positive feedback, although it's highly uncertain. It could be zero, and zero is a legitimate answer. I mean, don't think of zero as being a null result. The cloud feedback could be zero, and if the slope is zero, if there's no correlation in the data, then the slope is zero, and that's an answer. Or it could be reasonably large. And I've compared this with models, and the models kind of bracket the results of the data. But this is the global average. So we want to go the next step. We want to sort of ask the question, well, what does this really tell us about what's going on? And so the first thing we can look at is, I'll skip this. Let's look at the latitudinal distribution of the cloud feedback. And so these plots, the long wave feedback is on the left and the short wave feedback is on the right. And the measurements are in the solid line using two different reanalyses. Remember, these are the cloud feedback is calculated by using series measurements, and all the cloud information is in there. And then the reanalysis is used for the clear sky parts of it. And so the measurements, what I'll call the observations, are in the solid line. That's a series plus the reanalysis. And then there's an ensemble of climate models. That's the dash line. And you can kind of see it looks like ENSO. ENSO is this big rearrangement of the circulation. So you sort of see positive feedbacks for Longwave in the deep tropics, and then negative feedbacks in the subtropics. And you see the exact opposite occurring for shortwave. So shortwave and Longwave generally disagree, and the models do a reasonably good job. I mean, they don't hit all the highs and lows, but they get the overall structure for the Longwave and the shortwave about right. And so that's sort of it's glass half empty, glass half full. I kind of look at that as reasonably good agreement. On the other hand, models could obviously do better. Now the problem is, I'm going backwards. The problem is when you look at the net feedback. So this is the net feedback where you add the long and the short wave together, and the solid lines are what I'll call the observations. Again, that's series plus reanalysis. And the dashed line is the models. And you see that even though the climate models are doing a reasonable job getting the global average right, and they're doing a reasonable job getting the long wave and the short wave right, the net feedback is much harder to get right because it's a small difference between large competing numbers. And so the models get a positive feedback in the tropics, whereas the observations show a negative feedback. And then in the northern hemisphere, high latitude out here, the observations show a pretty strong positive feedback, and whereas the models show a zero feedback here. And if you integrate over the globe, these agree. But it looks to me like, at least given the data that we have for 10 years, the models may be getting the right answer for the wrong reason. And so you want to sort of drill down even further, and you want to sort of ask yourself the question, what kinds of clouds are driving these variations? And so we're going to try a different technique. So we're not going to use sort of the Soudan and shell technique of adjusting the cloud radiative forcing. And we're going to go to sort of some direct calculations of the impact of clouds. You start with MODIS data. So this is a histogram of MODIS data, and it tells you how MODIS in each, you have optical depth bins here and you have altitude bins here. So, this is between, 1 and 3 optical depths, 1,000 and 800 millibars. And this is the percent per degree of warming. So this says that clouds in this bin are increasing by about 0.5% per degree. And you can go and you can look in your favorite clouds if you like high clouds or mid-level clouds or low clouds. And you can see how they increase or decrease as the climate warms. And this is from Terra MODIS, and this integrates over 45 north to 45 south. But obviously we have this data granulated at any layer you want. And so then what we do is we take these observations of how clouds are actually changing as the surface temperature changes, and we multiply this by a kernel that Mark Zelinka kindly provided me. And what he's done is he said for a 1% change of clouds in any of these bins, how does that affect top of atmosphere radiation? So he has a long wave kernel and a short wave kernel, and you can kind of see the long wave kernel is mainly a function of how high the clouds are, and sort of more weakly a function of optical depth. Whereas the shortwave kernel is mainly a function of optical depth. It doesn't really matter how high the clouds are. And so then what you can do is you can take the observed change in clouds and you can multiply it by this kernel. This kernel tells you how much each of these changes is actually going to affect the top of atmosphere flux. And then you can integrate this however you want to do it. And so let me begin by showing, okay, so this is the kernel derived, the cloud kernel derived feedback as a function of latitude. And so this is a short wave, negative here, and positive here, and here's long wave, looks the opposite of that, and here's the net. And so let me put on the other method where I use the Soudan shell method to adjust cloud radiative forcing. And it's a bit of a mixed bag. At low latitudes, the two methods agree quite well. At high latitudes, there's definitely something odd that my graduate student Chen Zhao, who's done, I should give him credit, he's done essentially everything. I just give the talks. We're still working on what this is. It could be due to high latitude cloud retrievals. It could be due to multi-layer clouds. There's lots of ways, lots of issues. My guess is that the Soudan shell method is probably more accurate. If I had to bet on one, I would bet on that method. So I take places where they agree as places where I can use the cloud kernel method to try to look at how the feedback is broken down among clouds. And so what I'm going to do is I'm just going to show now 45 to 45, since we don't really understand what's going on poleward of 45. All right, so this is about the same plot I showed before. The dashed line now is, again, the total cloud feedback derived from the kernel method, where I sum up the impact of all the individual clouds. And so what we can do now is put on the contributions from high, medium, and low clouds. And so the black line is a contribution of high clouds. You see that when you look at the short and the long wave, they're almost entirely driven by changes in high clouds over the last 10 years. Now, for long wave, that's not surprising. You expect the long wave feedback to mainly be a function of high clouds because, it's the temperature difference between the cloud and the surface that really does that. I was a bit surprised that it was also really dominated as shortwave, but it is what it is. And you see that low clouds and mid-level clouds make very little impact in the long wave, and maybe a bit more in the short wave, but they're not near the dominance of the high clouds. But what's interesting is that if you look at the sum of them, what you see is that the high cloud, long and short wave cancel out almost perfectly. And so in the net feedback, mid and low clouds are just as important because they don't cancel between long and short wave. You don't get the cancellation that you do for these high clouds. And so if you sort of start looking at the importance of the clouds for the net feedback, it is true that the low and the mid-level clouds are as important, if not more important, than the high clouds. All right, so I'll just conclude with one thing and mention in 30 seconds why then you get so much scatter in the relationship. If you remember the plot I should begin of temperature versus the amount of energy trapped by clouds, it was just looked like a shotgun hit it. Maybe a shotgun tilted a little bit with a positive slope, but nonetheless, there was not a lot of it wasn't a clear plot, and it didn't give you a lot of confidence. And what I've come to conclude is that this is really a fundamental problem of the cloud feedback, that you have these two big terms that are canceling each other, and if there's a little noise on those, then the residual is also going to have a lot of noise. This is from a model that has a pretty small cloud feedback, and this is 70 or 80 years. You can see the long wave has a slope. Short wave, has a lot more scatter, but maybe there's a slope. You add them together, you get something that doesn't look like it correlates. And you could conclude from there that clouds don't correlate with surface temperature, but that's not really right because you see the long wave really does have a pretty good correlation. Instead, it's a consequence of the cancellation between these terms and the huge amount of noise, particularly in the short wave. So I'll sort of conclude. I'll go through this very quickly. Cloud feedback over the last 10 years is likely positive. I didn't really show that in here, but I think that's a reasonably robust conclusion for covering the data we have at least. And I showed a new method using cloud kernels, and they agree pretty well except at the high latitudes. We're working on that. It's sort of interesting to me, the short and long wave feedbacks are dominated by high clouds individually, but they cancel out in the net. And because of that, mid and low level clouds are important in the net, even though they're not that important in either of the individual feedbacks. And the scatter is this really fundamental problem, which it arises because you're looking at a difference between two pretty large terms. If there's some noise on them, when you subtract those terms, you're going to get something really noisy. And I don't know that there's any way around that. Thanks.
Thank you. Just one quick question, if you like. Okay. Thank you very much.